Hello, everybody, to one more session of Paul. Today, it's our pleasure to have Alina Stancu from Concordia University in Quebec, who will speak to us toward a fundamental gap of convex sets in hyperbolic space. Alina, thank you.
Thank you very much. Thank you for the invitation, and thank you, Beatrice, for all the logistic. And I apologize to the several people in the audience who already heard this talk in different versions. So this is based on work on with a group of collaborators that resulted in three papers. So Theodora Burni, Julie Clutterbach, Hainan Nguyen, Guofang Wei, and Valentina Wheeler. And it's about a spectral problem of the Dirichlet Laplacian. But let me start with just one-dimensional case, which is super simplistic. So basically, we're looking for a function and the real number simultaneously, function on an interval, and satisfying the equation u double prime plus lambda u equals 0. So there's an eigenvalue problem on 0D with the boundary conditions. The function at the endpoints of the interval is 0. And I bring this up because that's something that one can do in an undergrad course, and using the characteristic polynomial, you realize right away that the only type of solutions that could work with those Dirichlet boundary conditions, or here just boundary conditions, are the positive lambdas. And in that case, the functions, the first eigenvalues are lambda 1 and lambda 2, as described here, and with the corresponding eigenfunctions. And what's interesting is that the difference between the two eigenvalues is 3 pi square over d square, where d is the length of the interval. And it's also a very easy exercise to see that, in fact, it's the length of the interval that matters. You can change it to AB as long as the difference between B and A, the difference between A and B is d, then you get the same type of, you get exactly the same difference in terms of the length of the interval. And generally, so the problem corresponds to a domain in Rn. So connected compact with piecewise smooth boundary, and we take the negative Laplacian because we want the eigenvalues to be positive. So we set up the eigenvalue problem, Laplace u plus lambda u equals 0 on the domain, and the boundary condition is the Dirichlet type, so the function has to be 0 on the boundary. And it's known that that the spectrum, so the eigenvalues form a discrete sequence. The first one is strictly positive and simple, and then they diverge to infinity, they grow, they could have some multiplicity, etc. The fundamental gap of a domain is defined as the difference between the first two eigenvalues, and it has some physical interpretation in the sense of the amount of energy needed for a particle to go from the second state to the ground level state. I'm not actually very familiar with the physical interpretation, but that's one of the questions that I get quite often. And now, more generally, if omega is a domain in any Riemannian manifold, one can write the Laplace Beltrami operator and using the metric. And so if the metric, so I represent the metric as a matrix, Gij, the upper Gij will be the inverse, the entries of the inverse matrix. This is a positive definite matrix, and you can actually write the Laplace in coordinates, and writing the Laplace eigenvalue problem. In fact, it's going to look like an elliptic PD in coordinates in Rn, but in fact, it's not going to be exactly the Laplace operator as we saw it in Rn. It's going to have a first order term. And so no worries, I'm mentioning this because I know most of the people come from analysis, and so I just want to say that the typical cases will be considered here in this talk is just besides the Euclidean space, the spherical case, when you can think of the usual parametrization with the hyperspherical coordinates, and the hyperbolic space where one can think of the matrix Gij as being the diagonal matrix with 1 over xn, the last coordinate. squared on each of the elements of the diagonal. And so in fact, it doesn't matter which Riemannian manifold you get, in particular for this with constant sectional curvature. The spectrum, so the set of eigenvalues to this problem, the problem has exactly the same description. It's a PDE with the boundary condition, and the spectrum will be a discrete set of values with the first one strictly positive and simple, and the second one therefore different than lambda 1. And so therefore one can ask again about the fundamental gap as being the difference between lambda 2 and lambda 1. What is it? How does it pertain to the domain, etc. It's in fact this result on the spectrum. It's more general. Could be it's discrete, and it's of this form for any for the Schrodinger operator, where you add a potential function v, a positive function, and there are some results when v is convex as well. That will be pertinent a bit later in our talk. So first, let me say a couple of results about the upper bound on the fundamental gap, because they have the feeling or they give a sense of isoperimetric inequality. First, it was a conjecture. It was a Payne-Polya-Weinberger conjecture that in any space of constant sectional curvature for any bounded domain, and not necessarily convex, then the fundamental gap is bounded above by the fundamental gap of a ball, where the first eigenvalue of the ball is the same as the first eigenvalue of the domain. So this is kind of a normalization constraint, and then you can regard the inequality as an isoperimetric inequality. And so I mentioned here that convexity is not needed, and I wanted to make also a point regarding convexity on non-Euclidean or any other manifolds than Rn. Here the convexity, if it's mentioned for the first part of the talk, will be convexity as follows. A domain omega is convex if and only for any 2 points in the domain. The geodesic segment between the points will be contained in the domain as well. So we'll call this a geodesic convexity definition, and we will see that in some spaces one can define different type of convexity of domains. And so what was called PPW conjecture was proved in different stages, first in the Euclidean case and soon afterwards on the spherical case for domains included in the hemisphere. And then later by Ben-Gurion and Linde in the case of the hyperbolic space, so constant sectional curvature -1. And okay, and so let me give an idea of the proof, or at least some element that will be also pertinent for our talk as well. So if one wants to find an upper bound on the fundamental gap, so actually calculating the eigenvalues of a domain, it's usually very hard. One has some chances to get some information about the first eigenvalue of a domain, particularly if one uses some symmetry, radial symmetry, or separation of variables, but in general it's very hard. And so it's even harder to find the second eigenvalue. But if one wants an upper bound, it's very handy the fact that the eigenvalues have a variational description through the Rayleigh quotient. And so one starts with λ1 as a minimum of the L2 norm of the gradient of a function. I put here the function in C2, but the space can be relaxed, and divided by the L2 norm of the function. So if you take the minimum of that ratio, which is in blue, that one will give you the λ1, and the function realizing the minimum will be the function that is the eigenfunction corresponding to λ1. And as you go to the next eigenvalues, you take the same type of quotient, but Now the space in which the function lies, it's always orthogonal to the subspace defined by the previous eigenfunctions. So in the case of the second one, you're looking for functions that are orthogonal to the first eigenfunction, and you check for the minimum in within that class. And so the idea for proving the PPW conjecture is to use, at least this is the idea from Rn. It's easier to describe here. Let V1 be the first eigenfunction, and then take as a test function for lambda 2 a very well chosen function that's orthogonal to V1. So that will be a function PV1. So you take a function P that you construct in such a way that it's PV1 is orthogonal to V1, but also that kind of breaks somehow the symmetry. It's half symmetric in a way, and half it's destroying that symmetry to make a function that's not in fact that's not even strictly positive or positive as it was the first eigenfunction, and then using that test function, you can get an estimate of the difference of eigenvalues, as I said, by choosing wisely this P, you get the upper bound being given by the difference of the fundamental gap or the eigenvalues in the case of the balls. And so let's now get to the actual problem that I'm interested in, which is the lower bound on the fundamental gap. And it carried, again, also a name, a conjecture, the fundamental gap conjecture, was given independently by Vandenberg, who was a physicist, and also Yao and Ashburn-Benguria. And it's given for a more general class of operators, which is minus the Laplace plus a potential function. But in what concerns our talk, it's on the Laplace operator only. And yeah, so the conjecture was that the lower bound has to be 3 pi square over d square, where d is the diameter of omega, and this it's exactly so this bound here, it's oops, this doesn't work. This bound here. Okay, my pen doesn't work. So it's exactly the ratio that you saw in the baby eigenvalue case for the interval, right? So 3 pi square over d squared, it's the constant that I started with. And okay, so also the lower bound. So if one thinks about the upper bound as an isoperimetric inequality and can say that the extremizer is a ball or are balls, then in the case of the lower bound, in fact, there is no non-trivial or non-degenerate set that or domain that realizes the lower bound. The lower bound is approached when the domain degenerates to basically to a needle. So I said there's a thin rectangular box. This is if you want in R2, but generally all dimensions will go down. So it's basically approaching an interval. And this is for potential v equals 0. So just for the Laplace operator with the Dirichlet boundary conditions. So the conjecture was in late 80s or mid 80s, and then there were some partial results, but the actual conjecture was solved very recently, or in some sense very recently. But there were some initial bounds. So Li and Yao used well, actually, Zinger, Wang, Yao, and Yao used a so-called Li-Yao gradient method, and they showed one type of upper bound, which is lower than the conjectured one, and that was later improved. And then in both cases, the key argument was the low concavity of the first eigenfunction, and we'll come back to this a little bit later. And finally, The conjecture was proved in 2011 by Andrews and Clutterbuck, where they used some parabolic PD methods, and later the proof was actually redone or changed, or new proofs were given without using the parabolicity or a parabolic type technique. But this was done also with some kind of improved control over the concavity or low concavity of the first eigenfunction. So they had some way of showing that there is a lower bound on how low concave this function is. Okay, so after the result was obtained in the Euclidean plane, in the Euclidean space, in different collaborators, in fact, some subsets of the group of people listed there, they showed that the same lower bound for the holds for the fundamental gap of domains that are convex in Sn. Okay, so and the generating bound, it's also the same. The generating case, it's also a very thin geodesic segment, or a very thin geodesic set that degenerates to a needle or to a geodesic segment. And so therefore, since this held for both the Euclidean space and the spherical case, it was natural to ask if you have it also for the other space of constant sectional curvature, the hyperbolic space. And so the starting point for us was this low concavity. So let me start a little bit by saying that just having the low concavity of the first eigenfunction, it's enough to obtain this lesser, let me see, why is this not working, lesser lower bound pi squared over d squared. And the way it works, it's that you look at the ratio of the eigenfunctions u2 to u1, and you look at the equation satisfied, the PD satisfied by this ratio, and the fact that the first eigenfunction is low concave gives you a comparison with a model operator, which is a one-dimensional model operator, very similar with the one I took in on the first slide. So in fact, when k is 0, when you are on domains in Rn, the equation I'm comparing with it's exactly u double prime minus plus lambda u equals 0. So I'm comparing the equation satisfied by u2 over u1 with a model operator, and from here you get that the bound on the lower bound on the fundamental gap is greater than pi squared over d squared. And to actually get a better to get the conjecture, you need to have much more finer estimates. So what happens? So this is what happens in the case when k is 0, when k is strictly positive. When k is negative, it's not that the model operator, the one-dimensional model, is not there. It's there, and the model has a low concave function itself. That's a one-dimensional function, so it's easy to check. But it's a function of one variable, so it's easy to check. But what happens is that you have domains in the even convex domains in hyperbolic space, for which the first eigenfunction is not low concave. Okay, so then this is not what happens in the spherical and the Euclidean case. So our first result was to show that there are convex domains in the hyperbolic plane, not even in any dimension, just in the hyperbolic plane, such that the lower bound is below the conjecture value. In fact, the starting point was a counterexample to a low concavity of the first eigenfunction. So we looked at the hyperbolic model of the Poincare half plane. We did change to polar coordinates simply because the type of domain you will see, it's pertinent to a separation of variables. So we changed to polar coordinates even if these polar coordinates are not geodesic coordinates in the hyperbolic plane. But the domain we worked with was from a paper by Schick, who used such a rectangular type domain. So here you see you have the arcs RQ and SP that are geodesic arcs. They are parts of circles, arcs of circles with a center on the x-axis, and then the other two sides of the quadrilateral RS and PQ. They are simply they are not geodesic segments, but they are the domain entirely. It's convex because any geodesic between P and Q will be curved inside. Okay, it will be a little bit like, oh, okay, be going like this. Oh, for some reason my pen is not working. Okay, so all right, so so she looked at this type of domain, and it was not a constructive example, but it was an example in which he showed that for some values of C, okay, so C gives you the opening on the width, like vertical width if you want, and on the opening of the angles theta 0 and theta 1. For some values you will find a certain quadrilateral on which the first eigenfunction of the Dirichlet Laplacian is not law concave. And in fact, here are the actual kind of the numbers for the theta 0, theta 1, and C. So you see they are kind of like it's using a little bit of an intermediate value theorem type of result. So we showed for this example, we showed that in fact the lower bound, there is a lower bound on the fundamental gap, which is smaller than the conjecture one. So it's 3 pi squared over 2d squared. And why we even bother this? Because remember, in the other two spaces, just having that U1 is law concave, you could show a bound which was 3 pi squared over d squared, I believe, in any case. So we thought that maybe law concavity is what prevents of the fundamental gap, or the lack of law concavity is what prevents the fundamental gap from having a lower bound, but that was not the case. Still not having a law concave function, you had a lower bound. And then of course it was not bigger than the conjecture one, but in fact we couldn't show that particular domain doesn't satisfy the conjecture lower bound, but by playing with these parameters, the opening on the vertical axis and the opening of the two angles, we found that for some values, again, you have that lambda 2 minus lambda 1 is smaller than the conjecture value of 3 pi squared over d squared. So it's all related to this type of domain that was considered by Schick in one example. And then we realized that looking a little bit closer to this problem, to this type of domains, in fact, we realized that we can show first in the hyperbolic plane and then in any dimension of the hyperbolic space that we can always find a domain with a fixed diameter. So for any diameter, we can always find an epsilon. For any epsilon, we can always find the domain such that the fundamental gap is sufficiently close to 0, so it's less than epsilon pi squared over d squared. So that kind of said that there is no fundamental gap in the hyperbolic space. And okay, so we took the domain that we started in studying Schick's paper, and we transformed it a little bit. It's now, okay, so the two angles on the two sides, they're actually equal. So this is a symmetric domain in terms of the angle of opening. And we changed a little bit the notation. So that's maybe why I bothered to put here the new notation. And we realized that, I mean, we looked at the separation of variables in the polar coordinates, and we wrote down the equation satisfied by the eigenfunctions with the Dirichlet boundary conditions. And one thing that we could show was that for the first eigenvalue, we can show that the function is not only that it's no law concave, it has two maxima. And the way we showed it, we moved from the Poincaré disk model to the Poincaré half-plane model to the Poincaré disk model, where this thin rectangular, well, looking like a rectangular domain was looking rectangular, as I said, in the plane. But then when you map it in the Poincaré disk model, you realize that it has a very thin middle compared with the distances at the other two, as you approach the other two sides, QP and RS. So in some sense, this domain resembles more a dumbbell domain in R2, in the sense of having more mass away from the middle and toward the extremes, toward the two sides QP and RS. So basically, the eigenfunction looks like the graph in blue you have here. In the middle, you have it kind of now very little mass, and the eigenfunction has very little mass. It's close to 0, but the two extrema tend to concentrate toward the other side. And I'm mentioning this because, and this is what happens for the dumbbell, sorry, in R2, because okay, this is not a convex domain in R2, but this is precisely why you will have an eigenfunction, a first eigenfunction, which has two maxima, and it's almost like the union of the two eigenfunctions for each ball glued together nicely in the middle. Basically, it's like this. And so for the dumbbell, you can see also that the second eigenvalue can be obtained like taking the first eigenvalue of the first ball and the negative or the reflection of the first eigenfunction, taking the first eigenfunction on the first ball and taking the negative of the first eigenfunction on the second ball, so you get something a little like that, and you get an odd function. And that odd function will be basically, well, first of all, it's odd, and the first eigenfunction is even, so they are orthogonal to each other, and it's easy to see that they have basically the same or very close Rayleigh quotient. So the difference between λ2 and λ1 on the dumbbell, it's close to 0. So we kind of replicated this idea on the domain in the Poincaré disk model by showing that the first eigenfunction is a function of two maxima, and then constructing a good test function, because again, for the second eigenfunction, you cannot find it exactly, but you can find a good test function to get an upper bound. And the test function was the first eigenfunction multiplied by something that's looking like this, a step function that we controlled very well in the middle, so that we can make the two Rayleigh quotients sufficiently close as we want them. So here you have the basic idea. The first eigenfunction is the one in blue, and the second eigenfunction is, or a test function that's being used in the Rayleigh quotient of the second eigenvalue is the one with the dotted line. And basically, by looking at the Rayleigh quotient of phi h1, this test function, minus the Rayleigh quotient of the first eigenfunction, we show that they can be made sufficiently close to each other by taking that step function. Well, it's not quite a step function because it has to be continuous. So taking that part where we join the two steps to be sufficiently defined on a sufficiently small interval. And so, okay, so when we got to this, we said, okay, so there is no lower bound on the fundamental gap for convex domains in the hyperbolic space. And this proof that's in H2 can be generalized in Hn, because in fact, what we use here, if we use hyperspherical coordinates, so what we use, it's the radial function and the radial direction, and we use the spherical direction. So we can do this in Hn with just a little bit more work. But the idea was that maybe the convexity that we're looking at in domains of Hn is not the right type of convexity. And I want to say that convexity, of course, in Rn, we have this basic definition of the segment. In Hn or any other manifold, we have this equivalent definition with the geodesic segment. But in Rn, we also have this definition with the line segment is equivalent with the definition that any set in Rn is convex if for every point that's on the boundary, there exists a support hyperplane passing through that point, the support hyperplane of the set passing through that point, and then the set is the intersection of all support hyperplanes. And we don't have support hyperplanes in Hn, but Santalo gave what he thought is the equivalent of half spaces in Hn as horospheres. So horospheres are spheres with, so they're actually, they don't exist, but they take spheres in Hn whose center goes to the boundary, to the ideal boundary, and those when the limit is therefore a horosphere. In some sense, if you look at the Poincaré disk model, you can think of the horosphere as being, or even like say in 2 dimensions, you look at the disk that's tangent to the boundary of the disk model. Okay, so here, if you look at the disk, the larger disk, which is the Poincaré disk model, imagine here a disk, a circle inside, that's tangent from inside to the big one, to the Poincaré disk model. That will be a horosphere, and the inside and together with the boundary is the horoball. And so those will be the equivalent of half spaces in the hyperbolic space. So then you can think that you can define what's called horoconvex sets as being intersection of horospheres, or in other words, a set will be horoconvex if for any point on its boundary there exists a support horosphere passing through it. And so that the sets that you get in Hn will be fatter, that the sets, the horoconvex sets that you get in Hn will be more than, will be fewer than the convex sets in Hn. They will also be convex sets in the underlying Euclidean space, okay, and they will be fatter than the usual convex sets in Rn, in the underlying space. Okay, I don't know if I'm gonna come back to this maybe a bit later. So horoconvexity is stronger than geodesic convexity. You can think of it in also in other terms, that for a set that's in omega, for a set that's in the hyperbolic space that's convex, it's enough that the geodesic, like if it's in 2 dimensions, that the geodesic curvature is greater than 0, but horoconvexity will mean that the geodesic curvature is greater than 1. Okay, so that kind of gives you an idea that horoconvexity is stronger than convexity, geodesic convexity. And so we asked this question if the fundamental gap could have a lower bound on horoconvex domains, and since they are more restrictive than the convex domains. And so unfortunately the answer is no, but basically it goes a little like this. First we showed theorem 4. Basically, we look at the geodesic balls of radius r in Hn. They are both convex and horoconvex. And we looked at the 2 eigenvalues of those balls because they're a little easier to estimate. And we showed that for any radius r of a geodesic ball in Hn, one can find the constant, or there is a constant depending on dimensions, such that the fundamental gap is bounded above by the constant divided by r cube. So therefore, when you pass, so the bound that was conjecture was was dependent on a constant over r squared. So if we move r squared to the left and we do r squared times the difference of eigenvalues, we see that to the left with the C over R on the right hand side, and if R goes to infinity, then this quantity goes to 0. So again, we don't have a lower bound on the fundamental gap even for geodesic balls. Something interesting though, the fundamental gap of geodesic balls is bounded below by a constant, I believe it's n-1 divided by sine hyperbolic squared of R. So maybe that is the right function to look at. Not d squared, but something like sine hyperbolic of d squared, d over 2 squared or something like this. So okay, so we showed that geodesic balls don't have a lower they don't have the conjecture lower bound for the fundamental gap, and using the bound on the geodesic ball, the equation 4, we proved in fact that even for horoconvex domains that are more general, as long as the diameter is greater than a certain constant, you have a similar behavior in the sense that the difference λ2 minus λ1 is smaller than a constant divided by d cube. So again, it's not d squared, it's d cube, and that makes it so that when d goes to infinity, the quantity λ2 minus λ1 d squared goes to 0 instead of being bounded below by a constant. And so where is this, first of all, why the lower bound on the diameter? That could probably be made even better, but was not really essential. But the idea of the proof is interesting because it's going back to the isoperimetric type inequality on the difference of eigenvalues. So we start, so these are the steps, pretty simple for the general theorem. We start with a horoconvex domain of a certain diameter, and we choose a radius, we choose a geodesic ball. So it will have a certain radius such that the first eigenfunction agrees, they have the same value. Then what is a property of the hyperbolic is horoconvex domains in hyperbolic is that the in radius and circumradius, so these are notions familiar to this audience, then they are bounded, they are going together, they are not very far apart at any moment, even for very large sets. In fact, there are no very large and thin sets, kind of. So the difference between the out radius and the in radius is bounded above by ln of 2. And so if gamma contains, okay, so we look at the in ball, the inner ball, the one inside, and we realize that the in ball will have to be greater than, has a radius that's greater than diameter over 2 minus ln 2, and the radius that we chose, the R gamma that we chose in the beginning by the monotonicity of the first eigenvalue has to be greater than d over 2 minus ln 2. And so together we wanted both of these, so that was the reason for taking the diameter to be greater than 4 over ln 2. So we have kind of a nice lower bound on the R omega. So if the diameter is greater than this constant, then the radius of the ball that has the same first eigenvalue as the domain is greater than d over 4. And so using this, we have Ben-Gurion's results, which says that the fundamental gap of a domain is a convex domain, but here you can think that the horoconvex is also convex. So the fundamental gap of omega is smaller or equal than the fundamental gap of the balls with the same first eigenvalue. And then we know that this by the theorem before, by this relation 4, we know that this is smaller than Cn, or constant divided by R2 omega to the power 3. So if again we take, and then R omega is greater or equal than d over 4, so we get basically the fundamental gap bounded above by C of n and d cube. So again, if we take the going to infinity, we have that the lower bound is going to 0. So that's basically the proof, and I think I finished a little bit earlier because my pen was not working, so I couldn't actually draw at some point. But let me know if there are any questions.
Yeah, thank you very much, Alina. As she said, are there any questions, any comments, remarks?
I want to add a couple of things actually now that I have a little bit of time. So we were thinking that, as I said, the function that one needs to replace d squared with maybe is different. So the conjecture is okay. So the conjecture is with a 3 pi over d squared, right? And so maybe there is a better, like a different function, like could be maybe sine hyperbolic squared of d or something like this, maybe possibly modifying the constant as well. But in fact, for very small ranges, for the geodesic balls, if r goes to 0, then r squared times the fundamental gap behaves, so goes to the same limit as in the Euclidean plane. So basically, if you look close enough in the hyperbolic, you could see that the geodesic ball behaved like the Euclidean ball. So it might be that it has to be a threshold between the functions. Maybe there is not a unique function that in terms of the diameter that gives you the lower bound. Maybe that's a case. Maybe one has to judge differently what happens at a small range and what happens at a kind of like large diameter kind of range. We're not sure. We're still looking, but we kind of, I mean, we're not really very hopeful right away that something can be said. So.
Can I ask, do you have a lower bound for intermediate D? Or is this clear?
Yeah, so right. So in fact, we don't have a lower bound except for the balls, the geodesic balls. So we don't know. We were trying to figure out if we can cook up some domain that will have a lower bound as well, but we didn't succeed. That will probably be in somewhat the larger range, although you saw that constant is not so big. The constant that we had in the theorem here, which was 4ln2 or so on, it's small, given that domains in the hyperbolic, they can go up to infinite diameter. So it's not that big, but yeah, but probably we would need some kind of bound to say something about it, to say some lower bound holds. We also thought about yeah, go ahead.
Oh, sorry. Do you suspect that the domains which are problematic are only the ones with very large diameter, or could it be that one with a bounded diameter still has?
Yeah, well, okay, even if the diameter is bounded, but if it's sufficiently large, I think it's a problem. But we also so we kind of believe we still have to look within the class of convex domains rather than the whole class of convex domains. And of course, if we find a lower bound in the class of convex domains, then we can go back and see whether there is any chance to be satisfied by geodesically convex domains. But then one idea was, well, the convex domains in hyperbolic that also convex in the Euclidean model of so maybe use some kind of, maybe use as test function some combination of well, it works for the first eigenvalue, but it doesn't work so well for the second eigenvalue. Use as a test function the test functions of the eigenfunctions of the Euclidean problem. Kind of do an interplay to find some comparisons between the eigenvalues of a horoconvex domain in hyperbolic with the eigenvalues of the convex, the same domain, but viewed in the Euclidean. And maybe try to get something along these lines, like the fundamental gap of omega horoconvex, it's bounded below by some function of d times the fundamental gap of the domain in the Euclidean space, or the same domain, but viewed as a convex set in the Euclidean, not in the and as I said, that using this interplay between the two domains works well for the first eigenvalue, but what doesn't work well is that when you pass to the second eigenvalue, the eigenfunction, it's hard to control that the eigenfunction remains orthogonal with a hyperbolic metric with the, I mean, in the hyperbolic space. But we're still looking, but as I said, we kind of we're not looking with the same intensity as before because we kind of ran out of some particular ideas to try.
I see. Are there any other questions or comments?
I may have a question, and I don't know if it's valid, but the question that I have is whether the concept of orthogonality here is used in relation of the correlation of the two eigenvalues. You know, if it can be applied in such a way as in some, I mean, some statistical approaches to response, you know, where we utilize eigenvalues and eigenvectors to find a correlation between the underlying variables or the underlying factors in those cases. But this is a more generic, conceptually mathematical. So the question is whether this, there could be the orthogonality issue can be associated with a correlation between the two eigenvalues and eigenvectors. So that's the question.
So yeah, okay. So the orthogonality we have is the one in the needed for the Rayleigh quotient. So it's the L2 orthogonality in the metric of the space. I did not think whether that I'm not sure exactly how, if I can write it as a correlation, like you know, probabilistic, right? You want to have a probabilistic approach. I didn't think of it. I'm not sure. Something, yeah, I could give it more thought.
Okay, that's fine.
Any other questions? Okay, if not, let's thank Alina again. Thank you very much for the talk.
Thank you.
I'll stop the recording.